Here is the structure we have been discussing, the two-terminal MOS structure with a bias VGB, a charge on the gate QG, an inversion layer charge QI, and a depletion region charge QB. And the total potential drop here is the surface potential CS. You recall from the previous slide that the surface potential CS versus VGB looks like this, and that it flattens out over here for the following reason. Once CS becomes large enough, the electrons start piling up here next to the surface, so a very slight increase in CS is enough to increase the electron concentration and QI a lot. So when you increase VGB, you demand a larger inversion layer charge QI, but a slight increase in CS is enough to give you that QI. So PCI doesn't have to increase much, and this is why CS flattens out for large values of VGB. This is characteristic of what we call strong inversion. This is the weak inversion region. The in-between region is the moderate inversion region, and this here is the strong inversion region. We are going to concentrate on this part now. So in this part, what is the most important characteristic as far as the surface potential goes? It is that the surface potential is almost flat, almost constant. It is not 2 phi f as you very often see in some books. It is 2 phi f plus a certain amount delta phi, which is significant. Actually, this is a realistic plot. So if 2 phi f is, let's say, 7/10 of 1 volt, delta phi here can be 2 or 3/10 of 1 volt. It's not negligible, especially these days that we're talking about very low voltage circuits, and the total voltage you may apply on a device might be a fraction of a volt, so you cannot be ignoring things like that. So now the total potential here in the strong inversion region is 2 phi f plus delta phi. And it is clear that delta phi is not exactly constant because this curve is not exactly flat, but more or less it is constant. It is convenient to use a single value for it, so we will assume that it is constant, and the total 2 phi f plus delta phi, in other words, the total value of surface potential in strong inversion will be phi 0. We say that the surface potential is pinned to a certain value in strong inversion. So this is the pinned surface potential value. And as I already mentioned, delta phi is not mentioned at all in some treatments of strong inversion, but I advise you to take it into account. So now I'm going to use this value for the surface potential, phi 0, inside the simple equation we had developed for the inversion region, which was this one. If you go back to our general treatment, we had developed this equation, which is valid throughout inversion, weak, moderate, and strong. Well, in strong inversion, we can replace CS by phi 0, and we end up with this. Now this, if you lump all of these terms into one, and you call the result VT0, this will turn out to be the so-called threshold voltage, then this equation can be written simply like this. So now we have our first very simple equation. The inversion layer charge per unit area is negative, of course, and is proportional to the oxide capacitance and the difference between the gate bulk voltage and VT0, the threshold voltage. And VT0 from here is given by this expression. So these equations are very commonly used in strong inversion. So what do you see? That QI is a first-degree polynomial in strong inversion. Let's plot this. This is the magnitude of QI, because QI itself is negative, versus VGB. And in strong inversion, which is over here, you see this behavior, a straight line that corresponds to this equation. Now, this straight line, if you extend it, it goes like this. It goes as the broken line over here, and QI becomes 0 when VGB is equal to VT0. So the equation is wrong there, because the exact behavior of QI, if you take our general inversion expressions, goes like this as the solid line. So clearly the equation is wrong over here, but you don't care because we said this is the equation for strong inversion, and strong inversion is from this point on. This is strong inversion from this point on. So the equation is accurate in strong inversion. The slope of this is Cox. Remember, I'm plotting the magnitude here. And one interesting thing that I should point out here is that Vt0, which is a parameter that appears in this strong inversion equation, it itself is below the values that correspond to strong inversion. In other words, the equation here is valid from this point on, but in the equation there is a parameter Vt0 which is outside strong inversion. Now, don't make the mistake to assume that as soon as VGB is above the threshold, you're in strong inversion. You are not. You need a couple of tenths of a volt before you get to strong inversion. We'll talk more about this later on. Notice that we have assumed a uniformly doped substrate, no implantation of other dopants for now. So everything I'm telling you applies to uniform substrates. So we have seen now that we can simplify the general inversion equations to get really simple equations in strong inversion. And in the next video, I will do the same thing for weak inversion.